Hi everybody, welcome to week 4 of our prep for AP Precalculus mini course lesson. Last week we started talking about function families and we focused primarily on polynomial functions. This week you'll see a lot of commonality with last week's lesson, but today, this week we're shifting to rational functions. Now if you look at the definition up here of a rational function, a rational function is characterized as a function where both the fraction, it is a fraction, rational fraction, where both the numerator and the denominator, get my pen to work, both the numerator and the denominator, let's see if I can get out of here. There we go, that's what I want. Move that. Okay, let's hope that this will get me working. A fraction where both the numerator and the denominator are polynomials. So again, we are talking about polynomials, but we're now talking about a ratio of polynomials or a fraction. Sometimes it might not look like a fraction if the bottom polynomial is just a constant, but that is definitely a major takeaway when we're talking about what a rational function is. It is a ratio or fraction containing a polynomial on top and a polynomial on bottom. So the very first skill that we're going to practice today would be to simplify rational functions as well as to perform operations with rational functions. And we are going to, when we talk about operations, we're referring to adding, subtracting, multiplying, and dividing. Now in this section we're not solving. That will be in the next section after. We're just practicing simplifying, adding, subtracting, multiplying, dividing. You won't see any equal signs. You won't see any inequality signs. It's good that we practiced factoring last week because we will need that in order to do a lot of these types of skills. If there's a common factor, which could be a monomial, which is just a single term, a binomial or larger, that is in both the top and the bottom of the rational expression, then you can cancel out any set of duplicate factors as long as they're on top and bottom. That's what it means to simplify a rational. Now, when we get to multiplying, we will be combining the factors in the numerator, which is the top of the fraction, with multiplication, and we'll be doing the same with the denominators. And then we will try to simplify. If there's any canceling out or reducing of any type, we will do that. In a division problem, we treat it as a multiplication problem as soon as the fraction that comes after the division symbol gets reciprocated, which means flipped upside down. At that point, once you've done that with just the fraction that comes after the division symbol, then it becomes a multiplication problem like we'll have practiced. With adding and subtracting rational expressions, because they are a type of fraction, remember back to 5th and 6th grade math, adding and subtracting fractions requires a common denominator. So we will have to look at our rational functions that we're being asked to add, subtract, and we'll have to come up with a common denominator if there isn't already one. And then we will combine the numerators only with either addition or subtraction. So let's go ahead and practice some of these skills. The first thing that we're going to practice is just simplifying. And again, this does require factoring. So I'm going to practice factoring the numerator. Hopefully this is a skill that you feel like you've seen recently enough that it is going to be pretty effortless for you. I see these two factors on top and these two factors on bottom. If I see a common factor, which means the entire factor is identical on top and bottom, I can cancel them out. And what I end up with is a much simpler rational expression. And these are not alike. You cannot cancel out those x's because they are part of different binomials. You cannot cross out pieces of polynomials. It has to be entirely the same on top and bottom to do that. Our next problem is slightly different. Notice that we have a binomial on top and a monomial on bottom. What I do see is that on top, I have a GCF that I can take out. The biggest thing I can take out of this term and this term is a 27x to the third. What that leaves on top is an x from the 7x to the fourth, and a plus 2 from the 54x to the third power. So what I have now is a simplified, partially factored rational, where the top has been factored and the bottom never could be. But what I do see are two monomials here, and as long as they're the same type of polynomial, if there's anything you can do to cancel them out or reduce them, you can do that now. So x to the third can cancel out on both top and bottom, and 27 over 9 becomes just a 3. So I end up having no fraction left in my answer because everything down here got canceled out. So I have a 3 and I have an x plus 2, and that is my answer. If we look at the next problem, I see a difference of squares on top, so I'm going to factor that. And I see a GCF here on bottom. And what I'll notice is that there are no common factors on top and bottom. They're each their own unique factors. And so this cannot be simplified any further. You can either write it in its factored form, or you could even write it in its original form, but it is not possible. And that is always an option that these instructions will say, if possible, just to remind you that it's not always possible. Now we'll look at this problem, which is now a multiplication problem. That is the operation in this problem I can tell because of that times symbol. And so what I'll do is at each piece of these rational functions, I'm going to factor. And then once I have achieved any factoring that can be done, and again, there's always the possibility that there won't be, anything that's on the top and the bottom of the same fraction, or even fractions that are being multiplied or multiplied, if there's one in one fraction that's on bottom and one that's and the other fraction that's on top, because this is just a giant multiplication problem, and I'm just combining the numerators and combining the denominators, I see that there are definitely some things that I can cross out that are entirely the same. I have an x plus 9 and an x plus 9. I have an x plus 4 and I have an x plus 4. So in the end, my multiplied final simplified answer is just a simple x over an x minus 5. Again, these x's are not something that you can cross out because x would have to have a minus 5 after it up on top in order for this to be something that can be canceled out. Now here I see division, which just means that I'm going to flip this fraction upside down and turn this into a multiplication problem. So, and I'm also going to factor as I do that. So I'm looking at this first rational and factoring it. I'm going to put times, I'm going to put the x plus 4 on top, and I'm going to factor with a difference of squares this x squared minus 16. What I see is I have an x plus 4 on top and bottom, as well as an x minus 4 on top and bottom. And what I have left is a pretty simple looking rational answer. All right, let's look at this next problem. I'm going to scroll up a bit. Now we get to a slightly harder problem. It's just a more difficult level of factoring. It is a multiplication, so I don't need to flip anything. I'm going to factor, I'm just going to rewrite this underneath. I can take an x out of the first numerator, and that leaves an x squared minus 4. Now that itself, it can be factored as a difference of squares. So in the end, this will be my factored numerator. On bottom, I have a 4x squared that's already been factored out, and I have an x plus 10 times itself. There's nothing more, that's already factored. If I look at the next rational, I can see that I could take a 2 out of all of the terms in that numerator, and then the remaining trinomial is factorable. So I'm going to factor with an x plus 10 and an x minus 6. That's going to multiply together to get me that trinomial. And then on bottom, I see a pretty easily mental math level factoring problem that looks like this. So I've now factored everything. I see some things on top and bottom that can be canceled out. I have an x plus 10, and I have 2 of them down below. So I can cross out one of them from the bottom and the one that is on top. I also see a 2 and over a 4 that I can reduce to a 1 and a 2, and I see that this x can be canceled out with this, and I'll just make that a first power now for that x on bottom. So what remains on top is simply this 1, which I don't need to write, and this x plus 2. And what remains on bottom is this 2 that used to be a 4, as well as the x attached to it, and the x plus 10 that was the extra x plus 10 that had nothing else to cancel out with. This is a repeat problem, and I meant to change that, and I didn't. So I'm going to give you a problem that to replace this with. Actually, on your example, I will already have canceled it out. I'm looking here to see what I'm supposed to be doing here. I did that one. I'm drawing a blank on this one. What I meant to do. Okay, well, I guess we're just going to skip that one. So that's fine. We didn't really need it anyway. I was just giving a lot of examples. Okay, now we move on to the back page. Now what we see here is a combination of a multiplication and a division problem. You could have as many lined up of different multiplications and divisions as you want. You just have to make sure that this division sign turns to a times by flipping this fraction around. So let's go ahead and factor everything. In fact, I'm going to go ahead and do a preliminary GCF factoring here, because you'll see that that ends up being something that I can cross out of the top and the bottom. So if I were to factor this, I would have x minus 4 and x minus 6 over x plus 7, x minus 6. I have x squared minus 49, which is a difference of squares, over this, that is a minus 4 and a minus 7 at the end of its factors. This is now on top, x squared minus 49, which is factored this way, and I've got a 3 over another x squared minus 49 factored. So I have a lot to cancel out. I enjoy this. This is kind of satisfying. I have an x plus 7 and x plus 7. I have an x minus 7 and x minus 7. X plus 7, x plus 7, x minus 7. All I see is a 3 on bottom, which means that I only have a number answer. And that 3 on bottom has to have a number on top. If there's nothing else to join it, it's going to be a 1. Okay, so we've practiced our multiplication, division, as well as our simplifying. Now we're going to practice adding and subtracting. And if we look at this first problem, we notice that there is a minus sign here. So this is a subtraction problem. I must have a common denominator first. And I see that I do. So what that means is these are eligible to already be subtracted. The end answer will still have that denominator. And what I will do on top is I will take the first numerator minus the second denominator. And that minus will need to be distributed to both of those terms after they have the parentheses. So this would be a minus 7x and a minus 1. And then I reduce if I can. 8x minus 7x, 5 minus 1. This ends up being my answer. And we are done. All right, the next one, we have an addition sign. So we are being asked to add. I do not have a common denominator. I have a binomial here that's x minus 1. I have a binomial here that's x plus 2. I must have a common denominator. And so what I'm going to choose is one of each, x minus 1 and x plus 2. That's what I need. So I have the x minus 1 in the first rational, but not the x plus 2. So I'm going to multiply the top and the bottom of that fraction by x plus 2. The second rational is missing the x minus 1, so I'm going to multiply the top and the bottom by x minus 1. I would keep the denominators factored so that I can see that they are the same. This is an x plus 2 and an x minus 1 on bottom. And what I have on top is a new numerator, which is 3 times x plus 2 from the first rational. And the second one, I have a binomial. Oh, that's not supposed to be a 2 right there. I'm sure that confused you. That's just an x minus 1. I'm going to go ahead and take this 2x plus 7 and this x minus 1 and multiply them together so that I've already done some of my simplifying work. So 2x times x, you're just using FOIL here. 2x times negative 1 is negative 2x. 7 times x is a positive 7x. That's going to be plus 5. And then 7 times negative 1. And then I'll distribute. And I'm just going to combine like terms. So I know I will have a 2x squared. I'll have a 5x here and a 3x here that'll add up to 8x. And I have a minus 7, and this ends up being a positive 6 that I need to combine with subtraction. And this becomes my simplified addition answer with that common denominator. All right, let's look at this next one. We have a binomial here, and we can even make it look like it just has a 1 underneath it. Minus this rational expression right here. So I need a common denominator, and x minus 7 is the only denominator that's really standing in my way of that. The 1 is sort of just a placeholder. So I'm going to need to multiply the top and the bottom of this rational by x minus 7. And when I do that, I'm going to use FOIL, box method, whatever. I get 7x squared minus 49x plus 2x minus 14. And then I have a minus 5. That is from the second fraction. And I'm going to just combine my like terms and see if there's anything I can do to reduce this. You should always try to factor the numerator. This one is not factorable, so we can just leave it like that. And then the last problem kind of gets into something that's going to help us in our next section. And that is, even when we're doing these simplifying, multiplying, dividing, as well as the adding and subtracting problems, it is important for us to always note what is in the denominator. Because the denominator gives us values of x that are not going to work in a rational solving scenario. The denominator, if you think about back to your fraction math in junior high, middle school even, what is the one number that can never be on the bottom of a fraction because we cannot divide by this number? And the answer is 0. So what are the values of x in these problems where we have x in the denominator that would make the polynomial on bottom equal 0? Those are our undefined values. Which values of x is the expression undefined? I would take a look at my denominator, I would factor it. I'm not so interested in the numerator here, and I know that this represents an undefined value. I cannot have x be 7. If I plugged a 7 in here, it would make this denominator equal to 0, as well as the number 9. So it says, for what values of x is the expression undefined? 7 and 9. Those are my two values that I cannot plug in for x. That leads us into our next section, which is on solving rational equations or inequalities, where we actually have an equal sign or an inequality sign, and we're actually coming up with answers about what x equals or what it has to be less than or greater than. So in order to solve a rational problem, it is best to convert all pieces of the equation on both sides into rationals that have a common denominator. That's what we just practiced doing. Once it is achieved, all of the rational terms will need to be multiplied by that common denominator. That will eliminate the fractions, and then we will just be solving. But what we do have to make sure is that we've already noted any undefined values that the solutions cannot be. And we do that by solving each unique denominator to locate undefined or unallowed values. So I could look at this equation right here and go, look at that denominator, some of those denominators that contain x. What would be the value of x in this denominator that would make the rational undefined? So I'm just going to make a little note to myself over here that I see that I cannot use 0 as a solution to this. So if I get an answer that includes x equals 0, I cannot use that solution because I already know it is undefined at 0. I cannot plug a 0 into this fraction or this fraction, and that therefore is an undefined value for x. There aren't any other denominators that give us anything for x. There's no other way to solve any of the remaining denominators where I wouldn't get a solution of 0. So 0 is my undefined value. It's not asking me for that. It is a good first step before you start solving a problem. That way I can check my solutions on the back end to make sure they are allowed to be used. So if we look at this problem here, we see a 7x as a denominator in our first rational. We're going to be subtracting it from another rational. So I'm definitely going to need a common denominator to subtract these two. On the other side, I have a fraction, also considered a rational function, but I'm going to want to achieve the same denominator on both sides. So what would be the easiest denominator to have on both sides? It would be, and now my pen doesn't want to work. There we go. My least common multiple that I want to use is a 7 and an x. I need to make sure that these three denominators all have a 7 and an x. The first one does. That means I don't even have to touch it. The second one needs the 7, so I will multiply the top and the bottom by 7. And this last one on the other side needs the x, so I'm going to multiply by top and bottom by x. So now what I have is a combined numerator with subtraction, 2x minus 5 minus 14 over 7x. And on this side, I have an x over a 7x. I'm now going to multiply both sides by that denominator, which will just cancel out the fractions. And now what I have is my first numerator. If I combine those terms on that side, it's a minus 19. And I have my numerator on the other side. And this takes one step to solve, and I get 19. Is that an allowable solution? Well, the only one that's not allowed is the number 0, so I can circle this answer with confidence. We can also take this number and plug it in for x, and you would see that, let's just practice that once, just to remind you that you can. This should be a true statement. So if I were to take 2 times 19, which is 38, minus 5, is 33 over 19 times 7, which is 133. If I were to put this in a calculator, this left side would equal 1/7, and that's how I know I would have done it correctly. Okay, let's look at the next problem. I see a whole number. I'm going to stick a 1 underneath it. I see a rational that I'm adding to that whole number, and on the other side I see a rational on that side as well. So I need a common denominator, but first let's go ahead and determine what is a value or values of x that are undefined. I'm only looking in the numerators, and the only value of x that would make either of these denominators containing x equal to 0 would be the number 7. So remember that. When I get my solution, if it's a 7, I can't use it. Now what I do want to achieve is a common denominator. And so x minus 7 is the denominator for 2 of these. All I need to do is make the other one that only has a 1 on bottom have that same denominator. So I'll multiply the top and the bottom by x minus 7. Once I do that, I can combine the numerators on top with addition like it asks, and then I'll multiply both sides by the denominator that is the same, which cancels it out. So on this side, when I combine like terms and I bring everything to one side, I end up with x equals -1. And since that is not one of my undefined values, I can trust that that is a solution that works. We have one more problem similar to this. Now I have an x plus 7, so that means I only have, again, one undefined value, and it would be -7. That's the number that if I plugged into the denominators here, I would get a 0 denominator, which is not allowed. My common denominator, my least common multiple of these three, would be x plus 7. I'm going to multiply the top and the bottom of that first rational that doesn't have that denominator. So this will be an x times an x plus 7 minus a 1. And now I've combined these two into 1. I'm going to go ahead and multiply both sides by x plus 7, which just cancels out the denominator, and I will use distributive property. And then I'll move the 7 over. This is a quadratic, so it's best to solve a quadratic by moving everything to one side. And then I'll see that I have a x plus 8 and an x minus 1. And those factors have solutions of -8 and +1. Those are both allowed. Neither of them are a -7, which was my one that I was not allowed to use. Okay, let's look at our next problem. This is our last equation to solve. Now this is a harder one. If you notice, there's a whole number. There's a rational containing x plus 6. That tells me that one of my undefined values here would be -6. I can't plug that in for x right here and get something other than a 0. I'm going to go ahead and factor this other side. This would be an x plus 6 and an x minus 2. So what I see is that x minus 2 gives me another undefined value. I can't plug in a 2 into this quadratic on the right side, or I'm going to get a 0. So now I've got to look at what is my denominator going to look like. I have an x plus 6 that I must have, but then I also have an x minus 2 that I must have because of this guy right here. So this is the denominator I'm trying to achieve for all of the pieces of this rational equation. So the second fraction, or the second rational, I should say, it has the x plus 6. It just needs an x minus 2 multiplied to the top and the bottom. Whereas this one here, 1 over 1, it needs all of the above. It needs both of them on top and on bottom. Now, when I multiply those two together, I know what I'm going to get because it was my original denominator of the right side. So I'm going to put x squared plus 4x minus 12 plus, and I'll distribute a 5 to both of those things. Those cancel out. I'm multiplying both sides by those denominators. And then I'm going to consolidate on this side. I have an x squared plus a 9x minus a 22 equals 3x plus 5. And I'll take away 3x and I'll take away 5. And I end up with x squared plus 6x minus 27, which the factors would be these guys, and I end up with a x equals -9 and x equals 3, which are both allowed. Neither of those are undefined values. Okay, our last two solving problems involve solving inequalities. And this is a skill that AP Pre-Cal added last year. And so we're just kind of touching on it. We actually can use a graphing calculator on these types of problems. On the AP test, but it is something that's really good reasoning practice for anyone, simply because we know enough about rationals and the fact that usually these have a 0 on the other side. I'm just going to kind of walk you through how you could do this type of solving problem. So I think I'm actually going to come back to those after we do the last section, because I think you'll see that it talks about some of those properties. So we'll do that. The last section of the sections on the assignment, and therefore this lesson, deal with rational graphs, and it also how to determine the characteristics associated with a rational functions graph. There are some really important attributes or characteristics that we don't have in other functions that we do have in a rational function. We have to be able to identify if it has vertical asymptotes and what its equation would be. And vertical asymptotes always start with x equals. We also have to identify what other types of asymptotes it can have, horizontal or slant. They start with y equals. If you remember back from Algebra 2, we learned the acronym that's ridiculous, Bobo Batten eats DC. And we use that to help determine whether a rational has a horizontal asymptote, what its equation is if it does, or if it has a slant, also known as an oblique asymptote, and what its equation would be. So we have to think about asymptotes. That's a big, important concept here. We also have to be able to locate a hole if it exists. A hole exists if when you factor a rational function, if a factor cancels out on both top and bottom and is totally gone, or there still could be a duplicate left in the numerator in the top of the rational. If we do have a factor that cancels out on top and bottom and entirely, or is only left on top, then we have the ability to find the location of that hole by solving that canceled out factor for x and then plugging that value in to the simplified version of the rational function to get the y-coordinate of the hole. We also have to be able to locate any x-intercepts. If there are x-intercepts, they exist in the numerator, the factors of the numerator that don't cancel out as part of a whole, while a y-intercept, which there's never more than one of them, this is ever since we started learning about function types back in linear, you always just plugged in a 0 for x to get a y-intercepts location. The only time it won't have a y-intercept is if there's a vertical asymptote on the y-axis, which is this equation right here. So we're going to practice this. And the first thing we're going to do, they're going to ask us for just some attributes. Okay, so we're going to look at these vertical asymptotes, which are found in the denominator. So I see this right here. I want to solve that for x. I'll factor it first. I can set that equal to 0. The 2 will just be divided away, and I get x plus 9 equals 0. This means the equation of the vertical asymptote is this. The only reason it wouldn't be this is if this factor, x plus 9, had been in the numerator, and it's not. So we'll look at the next one. I'm going to factor both the numerator and the denominator. I have a difference of squares in the denominator. So if we look, there's no common factors on top or bottom, so these bottom ones will both represent vertical asymptotes. I have 2 in this particular rational. This one, I can factor the top. It's pretty easy. I can factor the bottom. Now here, I do have a cross out factor here. So that x plus 9 is not actually a vertical asymptote. It's part of a whole because it canceled out in both the top and the bottom and it's no longer there. So if you look at this, I don't have a variable in the denominator, which means this has no vertical asymptote. Now we need to turn our attention to our horizontal asymptote options. Remember that when we are looking for horizontal asymptotes, we're comparing the degree of the numerator to the denominator and using the Bobo-Botten-Eats DC. So if I look at the degree of the numerator, I have an x times an x, so that is a second degree polynomial. If I were to multiply all of the denominator together, I would have a 15x squared. So it is also a second degree polynomial. So what that means is this is an Eats DC. The exponents are the same on top and bottom, and so I'm going to divide the leading coefficients. And I'm not going to write this out again, this phrase. If I use the letters LC, you'll know I'm talking about leading coefficients. So this is an x times an x, so this is an x squared on top. This is an x times a 5x times a 3, and that's going to be a 15x squared. So these leading coefficients are 1 and 15. So my horizontal asymptote, which will always start with a y equals, is 1 over 15. I just divided those two leading coefficients. Now if I look at the next problem, I see I have a quadratic on top, and I have a linear on bottom. So if I have a bigger on top, then it means I have no horizontal asymptote. It is simply asking me for the horizontal asymptote, and the answer is that there is not one. I look at this next one, I have a degree of 1 on top, so this is a linear on top, and the degree of the bottom polynomial is 2. This is a bigger on bottom, which is a bobo, which means 0. 0 is the location of my horizontal asymptote. And then the next one gets us straight to talking about slant asymptotes. When we have bottoms with a degree of 1 higher on top, then that means instead of a horizontal asymptote, we have a slant asymptote. We will divide these, and we will be looking for what divides perfectly from the, or what is the part of this division problem that has, before I get to a remainder, in other words. So when we divide polynomials, which we practiced earlier in this summer's lessons, we're taking those leading terms and we are dividing them, and that's going to give us a 4x. And so I'm going to write that above the linear part of my divisor. I'm sorry, my dividend. And I'm going to multiply 4x times 4x and 4x times negative 3. And then I'm going to remember that I'm supposed to be subtracting these from what's above them, so that means changing their signs. This cancels out. This becomes a negative 12x. I bring down this last one, and the last term in my slant asymptote is going to be decided by this little quotient, this leading term by this leading term, and I get negative 3, and I'm done. At this point, I can write the equation of my slant asymptote has a slope of 4 and a y-intercept of negative 3. The remainder is not important. The only time you need the remainder pretty much is when you are actually just being asked to divide. This is asking us for the equation of the slant asymptote. I use division for most of that, but I don't need to finish the division problem. Now the next problem says, determine if the function below has a horizontal or a slant asymptote and explain why. Well, what I need to examine in this rational is what is the degree of the top and what is the degree of the bottom, and that's going to help me determine. So you do need to double check and make sure that these polynomials are in descending order. This one's not. This should be a 26x and then an 11 if I was really needing to verify. On the bottom it is in descending order, so I can easily look at the degrees of these two. So the top one has a cubic as its highest powered term, so that's a degree 3, and the denominator has a degree 2 for its highest term. So the degree is bigger on top. That means that there is no horizontal asymptote, but there is a slant asymptote. And that's because the degree on top is exactly 1 higher. The degree of the numerator is greater than the degree of the denominator by 1. And if they asked us to find the equation of the slant asymptote, I would be dividing these two in descending order. It doesn't ask me that here, but that's what I would be doing if they asked me to. Now this next one is the same type of question. I'm going to rearrange because I can see that these are scrambled all over the place. If I was being asked to divide, I would want these to be in descending order. I'm going to rearrange the bottom just a tad. So we have the same thing. We have a cubic over a quadratic. So this is another bottom, which means there is no horizontal asymptote. The degree is bigger on top. This means yes, we have a slant asymptote. And I'm going to use the same reason that was over here. This is my reason. I'm not going to rewrite that. Okay, now what we're going to practice doing, and this would involve an actual graph on Delta Math, but I don't have that part on here, but what we really need is just to identify these attributes if they exist, and that's going to allow you to plot those and move those around so that you can actually get your graph of your rational functions. So it says plot all of the existing 5 features. Some may not be needed, obviously, if there isn't a hole or if there isn't a horizontal asymptote, we wouldn't be using that. So they're asking us to find the vertical asymptote, the horizontal asymptote, a hole if it's there, a y-intercept and an x-intercept, or more than one if there is. I would suggest factoring these first. because that's going to help me. I can actually factor that quadratic a little bit more, like this, because I'm actually able to cancel something out. Now that tells me that there is a whole. Okay, and what my remaining function is, once I've factored and simplified, it looks like this, which means it may not even look like a rational anymore because there's no denominator left. But it does tell me I have a whole. And so I have a whole at x equals 1. So 1 comma something. I will take the remaining function and plug a 1 in for x. And that tells me that the y-coordinate of my whole is -6. Okay, because I set that canceled out factor equal to 0, that's what gave me the 1. I plugged the 1 into the remaining simplified rational, and that's how I got the y-coordinate. I could also do that very easily with the y-intercept. All I'm doing is plugging in a 0 into this reduced function, and I know that 0 comma -9 is my y-intercept. My x-intercept is found in the numerator. So the factor that has x in the numerator, which is the only part that has x in it, I'm going to set equal to 0, and I know that 3 comma 0 is my x-intercept. I have no vertical intercept, no vertical asymptote because I was not left with a denominator at all. And horizontal asymptote, I'm looking at the degree of the numerator, which was 2, the degree of the denominator, which was 1. This does not have a horizontal asymptote because the degree on top is bigger. So once you plot your x-intercept, your y-intercept, and your whole, then you're able to plot the rational function, and it should give you the correct answer. Now we're going to do this again. Now notice that this next option to the right offers a slant asymptote option, whereas the previous one did not. So that doesn't mean that you will need that, but it's there if you do. So we are going to work through this rational just like we did. If you end up accidentally graphing something or plotting something and it's wrong, you can always click on it again and that will remove it. So if we look at this, I'm going to go ahead and start with the horizontal asymptote. The degree on top is linear, so it's a first degree polynomial. Same thing with the bottom. So that means this is an Eats DC, where the exponents or the degree is the same. And I'm going to divide the leading coefficients, which are a 2 over a 1. This right here, that's my quotient. And so I get that there is a horizontal asymptote of y equals 2. That means there is no slant asymptote. Okay, there won't be both. Vertical asymptote. Is there anything I can do to simplify this rational expression, this rational function? There is nothing, there's no factor on top that is exactly the same on bottom. So I get to look at the vertical asymptote, the denominator for the location of my vertical asymptote, which is 4. My numerator, I will solve for x, and that will tell me that my x-intercept is at 4.5 comma 0. I can plug in a 0 for my y. I can plug in a 0 for x to get my y-intercept, and I get 2.25, -9 over -4. And there is no whole because I did not have to cross out, I did not have any canceled out factors. And once you plot those points and move the line for those asymptotes, you should be able to plot the rational function. All right, let's look at, we have a couple more. This one I'm going to go ahead and factor, which I can do more with. Now this one's a good one to show you because I crossed something out that I see on top and bottom, but there still is a remaining version of that factor on top. So we talked about what that would mean. That would mean that instead of, so x plus 2 being crossed out would tell me I have a whole. If there's still an x plus 2 and it's in the denominator, I would say that's, instead of a whole, it's a vertical asymptote. But because it's still in the numerator, I would say I can't use this. This cannot be an x-intercept because I've already said it's a whole. And you need to understand that if you have duplicate factors, this is the order, it's sort of a hierarchy. So if you're deciding whether something is a whole or an x-intercept, whole is going to win. If you're deciding if something is a vertical asymptote or a whole, it's not going to be a whole, it's going to be a vertical asymptote. So this right here is a whole, not an x-intercept. So I'm going to say that there is no x-intercept here. I won't be plotting anything, I'll be clicking that button. Now I also know that there is no vertical asymptote because I have no denominator left. And I also have a degree of 2 on top and a degree of 1 on bottom, which means that's a bottom, which means there's also no horizontal asymptote. So it's really important for you to see that sometimes none of these features end up being a part of the remaining rational. Now if we look at the next one, it's not asking me necessarily for values. It's asking me, not values, locations. It's asking me for how many there are of each of these things. And if you were to look at this function, it's a little bit more complicated. I'm actually going to factor this a little bit more, which means it's actually going to be a -6 over, next to an x minus 2, and the denominator is fully factored. So we're going to look at this. Horizontal asymptote. Okay. For us to know that, we have to compare the degree of the numerator to the degree of the denominator. The degree of the numerator, this is linear. The degree of the denominator has an x times an x that's being squared. So that's actually going to end up being a third power. So this is definitely a bobo, bigger on bottom, the degree, which means it has 1 horizontal asymptote, and that location is at 0. It's not asking me for that, but I could write that the 1 horizontal asymptote is at y equals 0. But this is how many it has. Now, are there any holes? Do I see any factor containing x that is exactly the same on top and bottom? I don't, so this has no holes. Vertical asymptotes, however, I see 2 factors remaining on bottom, remaining in the denominator. So I need to solve both of those for x. One of them is going to be x equals 4, and this one's going to be 1. I have 2 unique vertical asymptotes, so I'm going to put 2. My numerator, so I'm going to just say this is based in the denominator, this is based in the numerator. Any factor containing x that remains in the numerator that's not part of a whole, I can find by solving that factor for x. So I have 1 x-intercept, and then almost always the answer here is 1 y-intercept. But let's double check, because if I were to plug in a 0 everywhere I see an x, this would be -6 times -2 over 5 times -4 times 1. And so I do get a y-intercept of this value right here. Reduced, that would be -3/5. But the question's just asking me how many, and I would say 1. So these would be my answers: 1, none, 2, 1, and 1. Okay, now we're going to go back and look at the 2 inequality problems, because I kind of think we needed to go over these characteristics to really help us with this. So we are going back to our second page, the back of the first page, that says we're trying to make a sign chart that talks about how what x values is this rational function at or above the y value of 0. So that means at or above the x-axis. It's always good to note that that's really what that's saying if we're looking at a coordinate plane. So I'm going to solve the numerator for x, and that is my x-intercept. So that is definitely a location where the graph of this function would be on the x-axis. Now I'm going to solve the denominator for my vertical asymptotes, which are my undefined values. I don't actually touch these numbers. There's going to be a vertical asymptote there, and I see that 3x minus 6 that occurs 4 times. If I set that equal to 0 and solve for x, I would get 2. So at 2 right here. Now this is not, in fact, I don't even want to put that type of dot. I want to put, if I can get to my drawing tools. I'm having a hard time getting to those. Oh, that's definitely not what I wanted to do, but I'll take it. Okay, let me go back. Yeah. I really want to go back. I'm not really sure what I've done. That's not exciting. Let me try. Okay, I want to make this, I can scroll a little bit maybe. There we go. Let's do that. That's better. Okay, I wanted to make this, there we go, an open dot because it doesn't actually touch at 2. So here's the deal. I have x values to the left and including 0. I have x values between 0 and up to 2, but not including 2. And I have x values after 2. Our answer is going to be an interval notation. So what I'm going to do is I'm going to pick a number, pick numbers less than 0. I'm also going to pick a number between 0 and 2. And then I'm also going to pick a number greater than 2. So for the less than 0 number, let's just put in a -1. If I were to plug a -1 in for x, this would be 9 on top. It doesn't even matter what the number is. We just need to know what is the sign going to be. If I'm squaring something that's negative, it won't be negative anymore. If whatever this is ends up being positive or negative, when I raise it to the 4th power, it's still going to be positive. So I don't even care what the numbers represent. I care about it's a positive over a positive, and is that greater than or equal to 0? Is a positive number going to be greater than or equal to 0? The answer is always going to be yes. So this is going to be a positive value. All of this interval right here is going to be a positive value. Now, between 0 and 2, let's choose 1. I'm going to plug in a 1. 9 times 1 squared is going to be positive. Over 3 times 1 minus 6, that would be negative, but when I raise it to the 4th power, it's going to be positive. So I still have a positive over a positive. This is also going to be above the x-axis. And then lastly, I'll pick a number like 3. It doesn't matter what it actually equals. I just want to see, is it going to be positive or negative? This will definitely be positive. This is 9 minus 6 to the 4th power, which will be positive. This is also going to be greater than or equal to 0. All of this stays above or on the x-axis. The only place it doesn't is this undefined value of 2. So I can say that my answer is that all of the x values where this expression is at or above the x-axis would be all the way to 2 and all the way after 2. 2 is the only place where, if I looked at a graph of this function, I would have a vertical asymptote there. It's the only x value that I can't say has a value of where the corresponding y value is undefined. So I can't say it's greater than or equal to 0. Now we're going to practice this on one more problem. And then we're finally done. This is a very long lesson, I'm sorry. This next one is a cubic over a cubic. So I am going to do exactly the same step. I'm going to solve for x, solve the numerator, for my x-intercept, again, 6x to the third set equal to 0 is going to give me an x value of 0. So I'm being asked now to find when is the graph below the x-axis, meaning it's got negative y values. So 0 is a place where this graph potentially crosses the x-axis, x-intercept. And right here, if I solve the denominator for the vertical asymptote, I get -4. And I'm going to put an open dot there because that is undefined. It is not part of the domain. Okay, so I've got these splits. I've got this left side, I've got this middle section, and I've got this right side. So I'm just going to practice putting in some numbers. And again, the numbers themselves are not as important as their signs. So I'm going to, if I take a negative and I cube it, it's still negative. If I take 2 times -6, that's -12, plus 8 is -4. -4 cubed is a negative. A negative over a negative is a positive. That tells me what the signs of that side look like. Now let me plug in the -6. I'm sorry, -2 right here in the middle. 2 times -2 plus 8 cubed. So this top would be negative, because I'm cubing a negative, that keeps it negative. 2 times -2 plus 8 is a +4, and a +4 cubed is positive. So this is going to give me a negative value. And then if I were to pick a number bigger than 0, let's try 1. This would be positive over another positive, so that's going to be a positive answer. This question is asking me for negative y values. The only negative y values are going to occur here between our undefined value at -4 and our x-intercept at 0. And we are finally done. Thank you for your patience.